Imagine we have a graph with n vertices and 0 edges, so the number of connected components will be n in that graph. Let's start. We assume each vertex is a separate component. Now, let's add the edge from the vertex 1 to vertex 2. This will decrease the number of components by 1. This is because the vertices 1 and 2 are now in the same component. When we then add the edge from vertex 2 to vertex 3, the number of components will decrease by 1 again. However, when we add the edge from vertex 1 to vertex 3, this pattern won't continue. The number of components won't change because the vertices 1 to 3 are already in the same components. So this observation is the main intuition behind the disjoint set union approach. So the algorithm is, first, we initialize a variable to count with the number of vertices in the input, and then we traverse all of the edges one by one and performing the union find method to combine on each edge. So if the endpoints are already in the same set, then we keep traversing, and if the endpoints are not in the same set, then we decrement count by 1. So after traversing all of the edges, the variable count will contain the number of components in the graph. Let's say we have edges 1, 2, 3, 4, 5, 3, and 4, 5, and then we'll represent them into the node representation, which is node 0, 1, 2, 3, 4, 5, which is 6 nodes, n is 6. So there are 6 separate components, and each node represents themselves 0, 1, 2, 3, 4, 5. For example, 0 represent themselves is 0, and then we use a for loop to iterate every edge for i.e. range of lengths of edges. Then let's check the edge 1, 2. We'll try to connect node 1 to node 2, and then we compare the representative of 1 is 1 and representative of 2 is 2. They are not equal, so we can combine them into the same component. So we decrement the components variable from 6 to 5. And then node 1 and node 2, which one should become the representative? We just compare the size of 1, which is 1, and the size of 2, which is also 1. They are the same. So we just make the right side 2 become the representative. We assign 2 become the representative of 1, and then we increment the size of 2 by the size of 1, which is 1 plus 1 equal to 2. And then we check the edge 3 and 4. We try to connect node 3 with node 4. First, representative of 3 is 3, which is not equal to representative of 4, which is 4. So we try to combine them into the same component, so we decrement the component variable from 5 to 4. So node 3 and node 4, which one should become the representative? We just compare the size of 3, which is 1, which is equal to size of 4, which is also 1. So we just made the right side 4 become the representative, or assign 4 become the representative of 3, and then we increment the size of 4 by size of 3, which is 1 plus 1, which is 2. Then let's try to check the edge 5 and 3. We try to connect node 5 to node 3, and then let's compare representative of 3, which is 4, which is not equal to representative of 5, which is 5. So we can combine them into the same components, and we decrement the components variable from 4 to 3. So we have the node 4 and 5. Which one should become the representative? We just compare the size of 4, which is 2, which is greater than the size of 5, which is 1. So we make the 4 become the representative of 5, and then we increment the size of 4 by size of 5, which is 2 plus 1, which is 3. Then let's check the edge 4 and 5. We try to connect node 4 with node 5, and we compare the representative of the 4 is 4, which is equal to representative of the 5, which is also equal to 4. So they are already in the same component. We just return 0, and we can't change the component variable. It is still 3, but we have already finished the edge iteration, so we have to return these 3. So the combine method takes O of alpha of n time, but we do e times operation of combine method. So in total, the edges iteration take O of e multiplied by alpha of n time. So first, we have n for how many nodes we have and edges array, and we will use count components function for it, and it is in a class solution, and we will print them out as our output. So let's go back to define class solution, and we define a function count component. It has self, an argument n, which represents how many nodes we have, and edges array, and then let's create a variable representative array, which is one element array 0 multiplied by n, so it will represent every node by its parent. And we have size array, which is also 0 multiplied by n, which represents the size of territory of current node. And then we use a for loop to loop every node to generate the content for representative array and size array. So every node represents themselves. So representative at I is I. And every node territory size is 1 because it only contains themselves. And then let's analyze the complexity. The time complexity and the space complexity is both O of vertices to generate 0 multiplied by n in the array, in these two arrays. And then for generated content for representative array and size array, we'll call O of vertices time. And then let's create a variable component, which is n by default. That means they have n nodes. All of them is separate with each other and isolate themselves. And then we return components as our final result. We use a for loop to loop every edge. So in the ith edge, we try to combine the first node 0 and the second node 1. So to use the combine function, we also have to add another two argument, which is the representative array and the size array. So in the class solution, we go back to the beginning and we try to define method combine, which have self and representative array, size array, and the first vertex and the second vertex. So for vertex 1, we substitute it by its representative node. So how do we find its representative node? We will use the find method, and it will take two arguments, representative array and the vertex 1. And then we do the same thing for the vertex 2. So let's talk about the find method. When the node first time appears, the vertex is representing itself. So if the vertex is equal to representative at vertex, then we just return the vertex itself. So after combining, the vertex now have a new representative. So the vertex is not equal to representative at vertex. This is the vertex the second time it appears. We already changed its representative. So here, if we try to find the representative, we have to recursively call the find method for the representative at vertex. So finally, after we find the representative at vertex, we just return the representative at vertex. And then all of them is our find method. Now let's go back to the beginning and we try to define self, and they have two arguments, which is representative array and vertex. Then we check the first case. If the vertex is representative at vertex, that means the vertex is itself representative. At that time, we don't have to do anything, we just return vertex. So if the vertex is not equal to its own representative node, at that time we should try to use the find method to find the representative of representative at vertex. Then we assign them to the representative at vertex. And finally, we just return the representative at vertex. So let's talk about the combine method. If vertex 1 and vertex 2 after find they find the same representative, then they are in the same component. So after connecting, they will form a cycle and it won't change the components variable. If vertex 1 and vertex 2 find they have different representative, so they are separate components, right? So after combine, they will form into a one component. So we have to decrement the components variable by 1. If vertex 1 and vertex 2 have different representative, it have two combined directions. The first condition is the size of vertex 1 is greater than the size of vertex 2. In that case, we make the vertex 1 become the representative of vertex 2, and then we increment the size of vertex 1 by the size of vertex 2. Let's talk about the second condition when the size of vertex 1 is less than or equal to the size of vertex 2. In this case, we make vertex 2 become the representative of vertex 1, and then we increment the size of vertex 2 by the size of vertex 1. So in total, this is our combine method. So after we finish define find method, let's go back to the combine method, and this time we know how to find the representative node. So we have to judge the two cases. If the vertex 1 and the vertex 2 have the same representative node, then we return something. Or else, if vertex 1 and vertex 2 have different representative nodes, at that time we return another thing. So specifically, it divides to the two situations. If the size of the territory of the representative of vertex 1 is greater than that size of vertex 2, we do something, and else, if the size of territory of the representative of vertex 1 is less than that size of vertex 2, then we do something else. Because the territory size of the representative of vertex 1 is greater than that size of vertex 2, so we just combine the representative of vertex 2 into the data of vertex 1. Then we have to increment the size of vertex 1 by vertex 2 size, and then we just assign the vertex 1 become the representative of vertex 2. If the size of the territory of the representative of vertex 2 is greater than that size of vertex 1, at that time we combine the vertex 1 into the vertex 2, which by the increment the vertex 2 size by the vertex 1 size, and then we assign vertex 2 become the representative of vertex 1. So after we change the representative in the combine method, now let's go back to the count components method, and in the ages iteration, let's decrement the components variable by the combine method. If the vertex 1 and the vertex 2 have the same representative nodes, so they are in the same territory, so after combine they are still in the same components, so it won't change the components variable, we just return 0. And if vertex 1 and vertex 2 have different representative nodes, then they are in the separate components, right? So after combine, they were in the same component, so we have to decrement the size of components. In this for loop, we iterating every age, which requires O of E operations, and for every operation, we are performing the combine method, which is O of alpha of n. Well, the alpha of n is the inverse argument function, so the total time complexity of this for loop is O of E multiplied by alpha of n. So let's try to calculate the total complexity. The time complexity is O of vertices plus ages multiplied by alpha of vertices, and which is asymptotically equal to O of ages multiplied by alpha of vertices, and about the space complexity is O of vertices plus 1, which is asymptotically equal to O of vertices.